This is a cyclist taking a turn along a circular track. While taking a turn, the cyclist makes an angle theta with the vertical, or the cyclist bends with some angle theta. R is the radius of the circular track. Let us work from the frame of reference of the cyclist, that is the rotating frame of reference. In this frame of reference, the cyclist is in equilibrium. Let us talk about the forces acting on the system now from this frame of reference. The normal reaction will act from the ground on the system in the upward direction, which is perpendicular to the ground. I have shown that point A over here again. This is the normal reaction. Let C be the center of mass of this system. The system is the person along with his cycle. The gravitational force can be shown from the center of mass, that is C, in the downward direction, which is mg. M is the mass of the system. In this rotating frame of reference, we need to consider the pseudo force, which is centrifugal force in this case. And it will act from the center of mass in the outward direction, which will be mv square upon r. That is the centrifugal force. And static force of friction will act from this point A in the inward direction. I have shown that over here. Now why this force is static force of friction? Because this centrifugal force will try to skid this system away from the circular motion. It is the frictional force which is going to prevent it from skidding away. And hence this frictional force is static force of friction. Okay, yes. Now let us talk about why it is necessary for the cyclist to make angle theta with the vertical. Why it is necessary to bend while taking a turn. Suppose it does not bend. Suppose he is making a turn by not bending. So the angle theta is 0 degree with the vertical, like this. So in this case, the normal reaction will be upwards as before. And now the center of mass will be over here. And the gravitational force mg will act in the downward direction like this. So the normal reaction and the gravitational force will act along the same line. They will not produce any torque on the system. But the centrifugal force acting in this direction and the force of static friction acting in this direction are providing an anti-clockwise torque. This anti-clockwise torque will topple the system in this side. To prevent that from happening, the cyclist has to bend, make an angle theta with the vertical. In doing so, what is happening? That now the normal reaction and the gravitational force are not along the same line now. And together they are producing a clockwise torque, which will now balance that anti-clockwise torque of centrifugal force and static force of friction. This will prevent the cyclist from toppling away. Okay? Alright. Now let us write down the corresponding equations. We are working from the frame of reference of the cyclist. So the system is in equilibrium. So summation of all the forces should be equal to 0. So I am writing over here summation of F is equal to 0. Okay? Yes. So mg will be equal to n. Mg, that is acting in the downward direction, will be equal to the normal reaction and in the upward direction. Nv square upon r acting in the leftward direction will be equal to the force of static friction acting in the rightward direction. So mv square upon r is equal to Fs. Okay? Alright. Now as it is in equilibrium, it is in translation equilibrium, it is also in rotational equilibrium. Okay? So summation of torque is equal to 0. Now torque about what point? You can take torque about any point. Let us say torque about point A is equal to 0. Okay, So taking torque about point A, the normal reaction and the static frictional force will not contribute to any torque about point A. So the torque will be due to mg and mv square upon r. So the clockwise torque will be equal to the anti-clockwise torque. What is the clockwise torque? It is mg into AD. mg into AD, that will be equal to mv square upon r into CD. mv square upon r into CD. Okay, yes, over here m and m will get cancelled, correct? So AD upon CD will be equal to V square upon RG. What is AD upon CD? AD upon CD is nothing but tan of theta. So therefore tan of theta is equal to V square upon RG. So from this equation, for a particular value of velocity, you can find the particular value of angle theta. Okay, and it is obvious that as velocity is greater, the angle theta will be also greater. Correct? Okay. Now let us concentrate on this equation. Over here, mv square upon r is equal to fs. So if the velocity is greater, the static force of friction will also be greater. Correct? But we know that there is a limit to which the static force of friction can increase. That is the limiting force of static friction, which is also called as Fs max. And hence there is a limit to which this velocity will increase. Correct? So for maximum velocity, the static friction force will be also maximum. So how should I write down the equation? So over here I should write down m v max square upon r is equal to Fs max. And how much is Fs max? That is the maximum force of static friction. It is nothing but equal to mu s into g. Sorry, mu s into n. That is the normal reaction. So m v max square upon r is equal to mu s into n, which is the normal reaction, and n is nothing but equal to mg. Therefore m v max square upon r will be equal to mu s into mg. So here m and m will get cancelled. The maximum velocity with which the cyclist can take a turn comes out to be equal to square root of mu s r into g. Alright, and if the velocity is greater than this velocity, then the friction force won't be enough to provide the centripetal force. The cyclist will skid away. Correct? And let us talk about the angle theta made with the vertical when the velocity is maximum. Okay, yeah. So from here, velocity increases, theta increases. If v is maximum, theta will be also maximum. So tan of theta max will be equal to what? Will be equal to v max square upon rg. And what is v max square? It is mu s into rg. So rg and rg will get cancelled. So therefore tan of theta max will be equal to simply mu s. That is the coefficient of static friction.